My name is Dr. Safi Ahmed, and in this tutorial, I will discuss mechanical vibrations. We will discuss mechanical vibrations in terms of how engineers can use the principles of vibrations to make structures safe, and an application that is close to our hearts is the earthquake on 8th of October 2005. It was of magnitude 7.6, and unfortunately, more than 87,000 lives were lost, 19,000 of them being children in collapsed school buildings. This figure shows the earthquake damage in Balakot, and you see the rubble beside a building. And this figure shows a building also from Balakot from after the earthquake, and this building survived the earthquake. Here you see the infamous Margala Towers in Islamabad, and even though Islamabad was not at the epicenter of the earthquake, two of the seven towers collapsed. Now we note in these pictures that different buildings are in the same location or in the same apartment. They are built from the same materials and they went through the same earthquake, but some survived while others did not. So, as an engineers, we ask these questions: what can we learn from the buildings that survived, and how can we control the vibrations that cause disasters like this, so that we can prevent them in the future? And to answer these questions, we need to understand the concept of natural frequency. So, imagine you have a ruler held at the end of a desk, and you disturb it on the other end. You will notice that the ruler undergoes a certain vibration, and that vibration depends on the structure of this mechanism, such as the stiffness of the ruler, the length of the ruler, and how hard you have held it at the end of the desk, and material properties such as density, and the vibration that this ruler emits is known as the free vibration, and the frequency that corresponds to it is known as the natural frequency. Now, what do we mean by natural frequency, and how do we define it? Well, the frequency at which a system oscillates when it's disturbed from its equilibrium position and then allowed to vibrate freely without any continuous external force. And in simple terms, when you pluck or hit or disturb an object and let it go, the frequency with which it naturally wants to vibrate on its own, that frequency is known as the natural frequency. So we see an example of a guitar. If you pluck a string and then let it vibrate freely, it will vibrate at its natural frequency. Now, this phenomenon is not just limited to the basic minor structures, but also we see this phenomenon in mega structures, high rise buildings. Here you see a skyscraper on which you have the loads of wind, and if this structure is disturbed from its equilibrium and then allowed to vibrate freely without any continuous external force, then it will vibrate at its natural frequency. Now, how do we model these vibrating systems? Well, we have the spring mass diagram here that we use, and here m is the mass, and k is the spring constant, and x is the displacement from the equilibrium, and we neglect friction for this example. And we see here that when we look at the free body diagram and we do a force balance, we get the governing equation of this system. Now, this governing equation is a second order differential equation, and from the previous slide, we know that the response or the solution of this equation is in the form of a sinusoidal curve. So, we can assume x as the general form of a sinusoidal curve. Here, the omega n is the natural frequency of the system, as we saw in the previous slide. And to analyze this vibration system, what we can do is that we can take the derivatives of this expression of x and then plug it back in into the governing equation. And what we get after some algebraic manipulation is we get the expression for the natural frequency of the system. And we see that this natural frequency depends on the structural properties of the system. Here it depends on the stiffness and the mass. And what this suggests is that whether it is wind that disturbs a structure or an earthquake, as long as it is allowed to vibrate freely after the disturbance, then it will vibrate at its natural frequency. Now, what happens if this force is persistent on this mechanism? So, for instance, here we have a force of the form F naught cos omega t, where omega is the driving frequency being acted on this building in the form of an earthquake. How do we analyze such a system? Well, the hint here is that the forced vibration and the free vibration that we discussed earlier will superimpose for this building. Okay, how do we model that? Well, the governing equation for the free vibration is given here. And for the forced vibration, we will have the excitation force that we saw in the previous slide here on the right hand side. Okay, and the general solution of the free vibration system will be superimposed with the particular solution of this forced vibration system, and that will give us the general solution of this forced vibration system as shown here. And in this equation, we notice that we have in this denominator natural frequency as well as the driving frequency. And if we notice this form and we see what happens when omega, which is the driving frequency, approaches the natural frequency? Well, the amplitude goes to infinity. What this means is that the amplitude dramatically increases, and scientists name this phenomenon as resonance, and it is perhaps the most important concept in vibrational analysis. So, here you see the famous incident of the Tacoma Bridge. And what we see here is that the bridge is subject to the load of winds, which have the same driving frequency as the natural frequency of this structure. And we notice that the amplitude dramatically increases, and this is the view from the street level of the bridge, and we see how intense these vibrations are. And so if we notice in this expression, if we just can somehow bring another term here, that term can cap the effect of this term in case the driving frequency reaches the natural frequency. So, what can we do about that? Well, in our schematic from earlier, we can introduce the damping mechanism, or the damping constant, which, if we make the free body diagram and do a force balance, we get the governing equation, which has an additional term with the damping factor. And if we solve this differential equation under certain conditions, we get the following expression. And now note in this expression that we have a term alongside the omega n square minus omega square, which serves to cap the amplitude in case of a potential resonance event. So, alongside my presentation, I also have a material on training neural nets for vibration monitoring and safety, which can be accessed in the supplementary materials. The takeaway from this talk is that engineering is not about just the building strength, it is about the control that you provide to that building in terms of dealing with the incoming vibrations. And if such mechanisms had been implemented prior to the 2005 earthquake, nearly 87,000 lives could have been saved. And it's our duty as engineers to implement these mechanisms of free vibration, natural frequency, forced vibration, resonance, to implement these principles in our design. Thank you.